Let's wait for some more minutes for more participants to join. After that, I will start. এক্সাম টাইম তো এখন আসবে না। এক্সাম টাইম তো এখন আসবে না। অফ করা আছে। Please let me know if you can see my screen or not. So, hello everyone. Welcome to the NPTEL live session. Today is our 11th live session, and so we have almost covered everything which is there in the course. And today I'm going to revise all some of the previous topics. So today I'm going to solve some problems regarding shallow foundations. Uh, it will help to it will be a good revision. Okay, so the problems that I am going to solve today, I have already solved in lectures 1 and 2. In live sessions 1 and 2, I have solved those problems. Live session 1, 2, and 3, I believe. I have already solved those problems in details in those lectures. And I'm going to repeat those problems again as a part of this revision session. I'm going to repeat all those problems once again. Okay, so please pay attention. I hope this will be a good revision session. Okay, so let me introduce myself once again. My name is sinjandebnath. I am a PMRF research scholar in the Department of Civil Engineering at IIT Kharagpur. And so let's get started. So let's go to the first question. So let me read out the question first. So a strip footing of width 3 meter is founded at a depth of 2 meter below the ground surface. Okay, so in the question, a strip footing, okay, of width 3 meter is given, which is founded at a depth of 2 meter below the ground surface in a C5 soil. Okay, the soil is a C5 soil. Deposit having cohesion 3 C equal to 30 kPa and angle of shearing resistance phi equal to 35 degrees. Find the net safe bearing capacity of the foundation if the location of the groundwater table is first one 1.25 meter below the ground level and 1.25 meter below the base level of the foundation. Okay, so in this particular question we have been asked to find out the net safe bearing capacity of a foundation, and for two cases. Okay, for two cases. In the first case, the depth of the groundwater is 1.25 meter below the ground level, and in another case the groundwater table location is 1.25 meter below the base level of the foundation. Okay, so we have been asked to consider generally shear fillet theory of Terzaghi, and we have also been asked to consider the factor of safety of 3, and the unit weight of the unit weight of groundwater unit weight of soil above the groundwater table is given, which is 17.5 kilonewton per meter cube, and the saturated unit of soil is also given, which is 18.5 kilonewton per meter cube. Okay, so what is actually happening over here? Okay, in the first case, let me now focus on the first case. Okay, on case number A. So 1A actually. Okay, so in this particular case, the location of groundwater table is 1.25 meter below the ground level. Okay, so first of all, let me draw the problem. A strip footing of width 3 meter. Okay, so suppose this is your ground surface, and here is a strip footing, and the depth of the footing is 2 meter below the ground surface. Okay, so suppose you have a footing like this, and your footing is at a depth of 2 meter below the ground surface. Okay, it is a C5 soil, and cohesion of soil is, and the width is given, b is equal to 3 meter. Okay, and angle of shearing resistance and c is also given, so c is equal to 30 kPa, and phi is how much? Phi is 35 degrees. Okay, so we have been asked to find out the net safe bearing capacity of the foundation if the location of the groundwater table is number A 1.25 meter below the ground level. Okay, so groundwater level is somewhere over here. Okay, groundwater level is somewhere over here. This is the ground surface, and groundwater table is somewhere over here. And this depth, is how much? Is 1.25 meter below the ground level. Okay, so 1.25 meter below the ground level. Okay, this is the first case. So we have been asked to find out the net safe bearing capacity of the foundation. Okay, for this case. Okay, so now, so so now we need to find out the, you know, the overburden pressure at this level, okay, at 2 meter below the ground surface, that is at the base of the foundation level. Okay, so first of all, you need to find out the, you know, the overburden pressure. Okay, so suppose df. Okay, let me denote the depth of foundation by df. Suppose this one is df, 2 meter is df. Okay, suppose this is df, and the base level of the foundation, the depth of the base of the depth of the foundation is, suppose it is df, and the depth of ground water table is dw. Okay, let me consider that. Okay, dw is equal to 1.25 and df equal to 2 meter. Okay, dw is equal to 1.25 meter and df is equal to how much? 2 meter. Okay, so what is the overburden pressure at the base of the foundation? Okay, so you see, the unit weight of soil above the groundwater table. Okay, that means gamma. It is how much? It is 17.5 kilonewton per meter cube. Okay, and the saturated unit of soil is how much? It is 18.5 kilonewton meter cube. Okay, so gamma sat is how much? It is 18.5 kilonewton per meter cube. Okay, so what will be the overburden pressure at the foundation base level? So it is, so you can write it like this, right? So q is equal to, for the top portion here, we will use this one, that is gamma. So gamma into df minus dw. So sorry, so this one is how much? This depth of water table is dw. So gamma into dw. Gamma means the weight of soil, the unit weight of soil above the groundwater table. So gamma into dw plus, now this depth. Okay, so now this depth is how much? It is df minus dw. So, and what is the unit weight? It is submerged unit weight. Okay, so because it is submerged under the water. Okay, so df minus dw into submerged unit weight. And what is submerged unit weight? It is gamma sat minus gamma w. Okay, so now this one, we can also write it like this. Okay, gamma minus gamma dash plus tf gamma dash. Okay, we can write it like this. Okay, now I have been asked to find out the net safe bearing capacity. Okay, so now what is the phi value? Phi value is 35 degrees, right? So phi value is 35 degrees. Okay, so for phi equal to 35 degrees, so for phi is equal to 35 degrees, the bearing capacity factors, if you look at the chart, so we have been asked to use Terzaghi general shear failure theory. Okay, so if you look at the bearing capacity chart, bearing capacity factor chart of Terzaghi, you can find out the bearing capacity factor for general shear failure. So for phi equal to 35 degrees, the NC, that is the bearing capacity factor for the cohesion part, the first part of the bearing capacity equation. So what is the bearing capacity equation? So the general bearing capacity equation structure, it is like this, somewhat like this. For ultimate bearing capacity, it is generally like this. If we do not consider the shape factors, the depth factors and all, it will look like this, like, right? CNC plus gamma uh, dn gam, like it like this. CNC plus sigma dash nq plus half into gamma b n gamma, right? So for this part, this nc is how much? For phi equal to 35 degrees, this bearing capacity factors nc, nq, n gamma, all these factors depend upon the phi value, right? The angle of shearing resistance or the angle of friction. uh, the NC, NQ, and gamma all depend upon these phi values. So for phi equal to 35 degrees, if you look at the Terzaghi chart, or if you look at those equations given by Terzaghi, if you solve those equation, you will get the value of NC, NQ, and gamma. So value of NC is how much? It is 57.8, and NQ is how much? That is for the surcharge part. This NQ value, it will be like 41.4, and N gamma is like 42.4. Okay, so now you have all the values, right? You have the values of all the parameters of all the bearing capacity factors. Okay, so now uh, how much is this? Or how much is this? So gamma sat is how much? Gamma sat, it is already given in the question. So gamma sat is 18.5, right? So it is 18.5 minus gamma W is how much? It is 9.81 kilonewton per meter cube. So it will come up to be 8.69 kilonewton per meter cube. Okay. So now we need to use the for you know we need to find out the net safe bearing capacity, right? So we need to find out what the net safe bearing capacity of the foundation. Okay. So for net safe bearing capacity of the foundation, so for net safe bearing capacity of the foundation, first of all, we need to find out the net ultimate bearing capacity. Okay, in order to find out the net safe bearing capacity of the foundation, we need to find out the net ultimate bearing capacity first, and then after that, if we apply factor of safety on that value, we will get the net safe bearing capacity. Okay, so first of all, you need to find out the net ultimate bearing capacity, and after that, after getting the net ultimate bearing capacity value, if we apply a factor of safety which is given in the question, we will get the net safe bearing capacity. Okay, so so before that, let me just calculate the value of Q, that is the overburden pressure at the base level of foundation, that is Q value. So if we use this particular equation, if we this particular equation over here, okay, so dw is how much? dw, that is the depth of the water table. It is 1.25, right? So 1.25 into gamma minus gamma dash. So gamma is how much? It is given in the question. It's 17.5. So 17.5 minus of gamma dash, that is the submerged, is the how much? It is 8.69 over here. So 8.69 plus df. Df is the depth of the footing. It is how much? It is 2 meter. Okay. So 2 meter into that gamma dash is for the submerged unit, how much? 8.69. Okay, so now if we calculate this, if we calculate this, you will get the we will get the value of Q, and it comes out to be around 28.39 kilonewton per meter square. Okay, this value. So now we have all the values of all the parameters. So now we will use these values to find out the net ultimate bearing capacity. Okay, so net ultimate bearing capacity, that is QANU. It is denoted by QANU, right? So, so for QNU, what we do actually? So we just find out the net ultimate bearing capacity, and we deduct the overburden pressure part. Okay, that's right. Or the surcharge part. Okay, we just subtract that. So what will be like? So it will be like, so that means this part, and for QNU, it is like QU minus sigma dash, right? QU minus sigma dash. So it will be like CNC. So QNU is like CNC plus plus sigma dash NQ minus 1 plus half gamma B and gamma, right? So I will write it like this. So QNU will be CNC plus surcharge minus 1 plus half into gamma B and gamma, right? This one. So what is the value of C? C is mentioned in the question. It is 30 kPa. Okay, so 30 into NC. NC is how much? NC is around that's 57.8. So it is 57.8 plus sigma dash. That is the overburden pressure. It is how much? We have already determined that. We have already determined it over here. 28.39. So it is 28.39. NQ is how much? NQ we have already determined from the chart. It is 41.4. 41.4 minus 1 plus half into gamma. Okay, so gamma is the unit weight of this part. Okay, at the base of the soil, at the base of the below the base of the footing. Okay, below the base of the footing, and it is totally submerged. So we will use, since the base of the footing is totally submerged, so we will use, so the soil below the base of the footing is totally submerged, so we'll use the submerged unit value, submerged unit weight value of the soil. So it is this 8.69. So half into 8.69 into b, the width of the footing is how much? It is 3 meter. So 3 into n gamma. N gamma is how much? N gamma is around 42.4. Okay. So it is 42.4. So now if you just calculate this equation, you will get the value of QNU, and QNU comes, and it will and so if you calculate this, you will get the value of QNU, and so QNU is equal to 34.64 kilonewton per meter square. So 3433.64 kilonewton per meter square. Okay, so now we have the value of QNU with us. So now if you apply a factor of safety on this QNU value, you will get the value of QNS, that is the net safe bearing capacity. So we now have the net ultimate bearing capacity, and if we apply the factor of safety on this value, we will get the net safe bearing capacity. So QNS, so QNS equal to QNU by factor of safety. Okay, so QNU is how much? QNU is 3433.64. Their factor of safety is how much? It is given in the question. It is 3. Factor of safety is 3. We have been asked to consider a factor of safety of 3. So now if we divide this 3433.64 by 3, we will get the value of QNS, which is the net safe bearing capacity of the foundation. So QNS comes out to be around 1144.55 kilonewton per meter square. Okay, this is the answer. So this is the answer. So I hope you have understood this problem, the first part of the first problem. Okay, so I hope you have understood. Now let's move on to the second part of the problem. Okay, so now let's move on to the second part of this particular problem. So in the second part, so what is the second part? So in the second part, the groundwater table depth is 1.25 meter below the base level of the foundation. Okay, so that means in the second case, so suppose this is your ground surface, this is your footing. Footing is how much? The depth of the footing df is equal to 2 meter, right? The depth of the footing is 2 meter below the ground surface. Width is 3 meter. So width is 3 meter. And in this particular question, the groundwater table is 1.25 meter below the base level of the foundation. So groundwater table is somewhere over here. Groundwater table is somewhere over here. Okay, so it is 1.25 meter below the base of the foundation. Okay, and this is the DW. Okay, from the ground surface. This is the ground surface, and this is the groundwater table over here. Sorry, not here. At here, over here. Groundwater table. Okay, it is 1.25 meter below the base of the foundation. Okay, so now, so what is the equation? The net ultimate bearing capacity. So for net safe bearing capacity, first we need to use the we need to find out the net ultimate bearing capacity. Then after that, we will apply factor of safety on that to get the net safe bearing capacity. Okay, so what is the formula for net ultimate bearing capacity? That is QNU. So QNU is equal to CNC plus Q in Q minus 1, Q or sigma, anything you can write, that is the surcharge or over effective overload pressure, anything. So plus half into B n gamma dash. Okay, so gamma dash. So we need to incorporate the effects of water table into that. Okay, so how will you incorporate? Because you see, the footing, this footing is above the groundwater table, but it is only 1.25 meter below. The groundwater table is 1.25 meters below the base of the foundation. Okay, So it will have some effect, it will have some influence on the bearing capacity of the foundation. Okay, so how we will calculate that? So first of all, we need to find out gamma dash. Gamma dash, so it is how much? It is gamma submerged plus b by b gamma minus gamma dash. So what is b is this value, the depth of the water table from the base of the foundation. Okay, that is b. Okay, that is how much? That is 1.25. So we will incorporate, so we will just put all the values of all the parameters into this particular equation. So gamma dash, it is how much? We have already determined that. So this is gamma dash, it is 8.69. So 8.69 plus b is how much? B is 1.25 by small b. Capital B is how much? It is 3 meter. So gamma is how much? Gamma, the unit rate of soil, is how much? It is 17.5. So 17.5 minus gamma dash, that is the gamma submerged, is 8.69. So if you calculate this, we will get the value of gamma dash. So gamma dash comes out to be around 12.36 kilonewton per meter cube. Okay. So here what we are doing is that we are incorporating the effect of groundwater table into this gamma dash. Okay, gamma dash of the third part. Okay, so now if we just subtract, if we from this q in, if we just subtract this q, the surcharge, we will get the we will we have already subtracted, right? So we have already subtracted. So actually, if we subtract this q from the ultimate bearing capacity, we get this value, get this equation, that is the net ultimate bearing capacity. Okay. So now we need to use this particular equation to find out the net ultimate bearing capacity. Okay, so now let us put all the values of all the parameters. Okay, we have the value of C, we know the value of NC, Q, NQ minus 1, we have everything. Okay, so we just need to put the values of all the parameters into this particular equation. Okay, so QNU is how much? It is C and C. Okay, C is how much? C is 30. NC is how much? NC is 57.8. It is already written over here. I have already written 27.8, this value, and plus what is the overburden pressure or the surcharge at the base of the foundation. It is 28.39. This value 28.39 into NQ minus 1. NQ we have already found out over here. It is 41.4. So 41.4 minus 1 plus half into B and gamma gamma. So B is the breadth of the foundation is how much? It is 3 meter. Gamma, the N gamma, that is the bearing capacity factor. It is how much? N gamma is around 42.4. So 42.4 into gamma dash. Okay, so gamma dash, this part, it is how much? Gamma dash, it comes to it. So it is around, it comes out to be around 12.36. Okay, so 12.36 it is. So 30 into 57.8 plus 28.39, 41.4 minus 1 plus half into 3 into 42.4 into 2.36. So if we calculate this, we will get the value of KNU. So KQNU comes out to be around 3517. 0.05 kilometer per meter. So now if you just if we just apply factor of safety on this particular value, we will get the net safe bearing capacity. Okay, that is the QNS. It is QNU by F. Okay, so it is 3517.05 by factor of safety is how much? It is 3. Okay, so if we divide this by 3, we will get the value of QNS. So it comes to around 1172.35 kilonewton per meter square. Okay, so this is the answer. So I hope you have understood this particular question. I'm giving you 5 minutes. Please go through this particular problem. If you have any doubt, you can let me know in the chat box. Okay, so please go through this problem once. Okay, so I hope you have all understood this problem. So now let me move on to the next problem. So this is the next problem. So let me read out this problem once. So a rectangular footing. So a rectangular footing of size 2 meter by 3 meters. So it is a rectangular footing, size 2 meter by 3 meters. So this is B, the breadth of the footing. This is the length of the footing is founded at a depth of 2 meter in a homogeneous C5 soil layer. This is the depth of the foundation. So let me write down all the parameters over here. So breadth of the foundation is how much? It is 2 meter. The length of the foundation is 3 meter. The depth of the foundation is 2 meter in a C5 homogeneous soil. The water table is 1 meter below the ground level. So dW is how much? It is 1 meter. The unit weight of soil above the water table is 18 kilonewton per meter cube. So gamma is 18 kilonewton per meter cube. Okay. The saturated unit weight of soil is 20 kilonewton per meter cube. So gamma sat is 20 kilonewton per meter cube. Okay. And determine the rigidity index and critical rigidity index of the soil. Okay. So I have been asked to find out the rigidity index and critical rigidity index of this soil. Okay. So we have been asked to consider C equal to 50 kPa, that is cohesion, C equal to 50 1 minute. C equal to 50 kPa, and phi, that is the frictional angle, uh, is 30 degrees. Okay, 30 degrees. So modulus of elasticity of the soil is 5 MPa, that is E value. E value of soil, that is the modulus of elasticity, is around 5 MPa, and the Poisson's ratio is around 0.35. Okay, it is 0.35. Okay, and also the load is vertical and acts at the center of foundation, so that means there is no eccentricity. Comment on the correction factors due to soil compressibility. Okay, so first of all we need to find out the rigidity index and critical rigidity index. So after that, after comparing both the values, we will comment on the correction factors due to soil compressibility. Okay, so first of all we need to find out rigidity index, that is IR. So rigidity index, that is IR. Okay, IR. So first of all, we need to find out IR. So it is how much? It is G, that is the shear modulus of soil, divided by C plus Q dash, that is the overburden pressure at dF plus B by 2 depth. I will show you uh, into tan phi. Okay, this is the equation for to determine the rigidity index of the soil. Okay, so we know the value of C, that is the cohesion. Cohesion is how much? It is 50 kPa, and we can easily determine the value of Q dash, that is the Q dash, that is the overburden, effective overburden pressure at the depth of dF plus B by 2. dF means the depth of the foundation, and B by 2 means half of the width of the foundation. So dF plus B by 2, at that depth we need to find out the effective overburden pressure. We know the phi, we can easily find out tan phi, so G. Okay, so how we will find out the shear modulus of soil? We know Young's modulus and Poisson's ratio. Using that, we can use the relationship between Young's modulus, Poisson's ratio, and shear modulus to find out the shear modulus of soil. Okay, so let us do that first. So G value. Okay, so first of all, let us determine the G value. So G is equal to E by 2 into 1 plus mu, right? Or 1 plus nu. Okay, the Poisson's ratio. We know this, right? So E is how much? Is 5 kPa, I believe. E is 5 MPa. So 5 MPa means 5 into 10 to the power 3 kPa divided by 2 into 1 plus Poisson's ratio is how much? It is 0.35. So it is 0.35. Okay, so now if we calculate this, we will get the value of G. So value of G is the shear modulus comes out to be around 1852 kilonewton per meter square. Okay, so this is the value of the shear modulus of soil. So now we need to find out this value of Q dash. Okay, so Q dash at dF plus V by 2 depth. Okay, so dF plus V by 2 means dF is how much? So dF, the depth of the foundation is how much? It is 2 meter. V is how much? 2 meters. So that means 2 meter plus 2 by 2, that is 3 meter. Okay, so at 3 meter we need to find out Q dash. Okay, so it will be how much? So at 3 meter, so let me draw the footing here. So suppose this is your footing, this is the ground, this is your ground surface, and the depth of the footing is 2 meter, this 2 meter dF value, and this water table is 1 meter below the ground level. Okay, water table is somewhere over here, 1 meter below this ground level. Okay, so over here, so we need to find out the uh, effective overburden pressure at dF plus V by 2. So that means dF, this one is dF 2 meter plus V by 2 means B is how much? B is 2 meter. Okay, so 2 meter. So this is 2 meter. So half is how much? It is 1 meter. So 1 meter. So dF plus B by 2. Okay, so 2 meter plus 1 meter. This is 1 meter. So it is 3 meter. Okay, so at this step. So it will be how much? So Q dash will be how much? So it is around, it is like this part. This is 1 into this 18. So 1 into 18 plus 1 into 18 plus 1 plus 1. So 2 into gamma submerged. Gamma submerged means gamma sat minus gamma w. Okay, so this one is equal to, at 3 meter depth from the ground surface, it is 1 into 18. That means this part, this part above the groundwater table. So we'll use this 18. So 1 into 18 plus this portion into submerged unit weight. Okay, so this portion is how much? It is 2 meter. Okay, so 2 meter plus 2 meter into submerged. So what is submerged unit weight? It is saturated to the saturated is 20, so 20 minus 10 if gamma w is 10. So 20 minus 10. So now if you calculate this, you will get the value of Q dash, which comes out to be around 38 kilonewton per meter square. So now we have all the values. We have the value of G, C, Q dash, tan phi, everything. So we just need to incorporate that into this equation. So after putting all the values of all the parameters into, so after putting all the values of all the parameters into this equation, we will get like rigidity index. So IR is how much? It is G. So what is the value of G? It is 1852 kilonewton per meter square. So it is 1852 divided by the C plus Q dash tan phi. So C is how much? C is 50. C is 50 kPa. So 50 plus Q dash tan phi. Q dash is how much? It is 38 kilonewton per meter square. So 38 tan phi. Tan of phi. Phi is how much? Phi is 30 degrees. Okay, so phi is 30 degrees. So after calculating this, you will get the value of IR. So IR comes out to be around 25.7. Okay, so we have determined the value of IR. So we have determined the value of rigidity index. So after that, we need to find out the value of critical rigidity index. Okay, so in the we have been also asked to find out the critical rigidity index of soil, that is IRCR. Okay, so IRCR, this value. Okay, so there is the equation. So what is the equation? So it is half into exp, that is exponent 3.30 minus 4.50. Sorry, that 1 minute. So 3.30 minus 0.45 b by L cot 45 minus 5 by 2. Okay, this. So now let me just put the values of all the parameters into this equation. So half into exponent 3.3 minus 0.45 b. B is how much? B is 2 meter, L is 3 meter. Okay, so 2 by 3 cot of 45 minus 5 by 2. 5 is how much? 5 is 30 degrees. 5 minus 30 by 2. Okay, so this one. If you calculate this, you will get the value of IRCR. You will get the value of IRCR. So IRCR comes out to be around 90.3. Okay, so now see what is the value of IR. The value of IR we have already determined. It is around 25.74. Okay, so IR is 25.74 and IRCR is 90.3. So that means IRCR is greater than that of IR, right? IRCR is greater than that of IR, so that means the correction factors due to compressibility, that is correction factors due to compressibility, that is CC, CQ, C gamma, all this value will be less than 1. Okay, will all be less than 1 because you see the critical rigidity index is greater than the rigidity index of the soil. And if IR was greater than that of IRCR, then all the correction factors values CC, CQ, C gamma, all these correction factors values would have been greater than would have been equal to 1. Okay, so I hope you have all understood this particular question. Please go through this problem once. I hope you have understood, but still go through this problem once. After that, I will I'm giving you 5 minutes. Please go through this problem once again. So after that, I will resume this session. Okay, so I hope you have all understood this particular problem. So if you have any doubts regarding this problem, you can visit the previous lectures because all these problems are there in the previous lectures, in the previous live sessions. You can find the recordings on the NPTEL site. The link is given over there. And also, if you still have any doubts, you can just write that down the doubts in the YouTube chat box, and also you can write down. Also, you can post your doubts in the NPTEL forum, and also you can personally mail me. You can easily find my mail ID in the uh, description box of YouTube videos in each and every YouTube videos. Okay, so you can find my email IDs over there. So now let us proceed to the next problem. Okay, so okay, so now let us proceed to the next problem. So what is the next problem? So this is the next problem. So let me read out the question first. So a square footing. So a square footing fails by general shear. Okay, in a cohesionless soil deposit having pi equal to 40 degrees. Okay, so a square footing. Okay, a square footing. Okay, here it is a cohesionless soil, that means equal to 0, only phi is there. Phi is how much? It is 40 degrees. So a square footing fails by general shear in a cohesionless soil deposit having pi equal to 40 degrees under an ultimate load of 5500 kilonewton. That means 5500 kilonewton. Okay, so Q ultimate is how much? It is 5500 kilonewton. Okay, so this is the Q ultimate, the ultimate load. Okay, the ultimate load that the foundation can take. Beyond that load, it will the foundation, the soil will fail by general shear failure. Okay, so the footing is placed at a depth of 2 meters below the ground level. Okay, so the footing is, suppose this is the ground level, and the footing is placed at a depth of TF is equal to 2 meters below the ground level. Okay, this is the ground level, and given the unit weight of soil is 18 kilonewton per meter cube, and NQ is given, bearing capacity factor for this second surcharge part, it is 81.3, and in gamma the bearing capacity factor is given, it is 100.4. So we have been asked to determine the size of the footing if the water table is founded at a great depth. Okay, use the Terzaghi's theory. Okay, so water table, suppose it is at a great depth such that it water table does not have any influence on the bearing capacity of the foundation. Okay, so suppose we have been asked to find out the size of the footing, or suppose it is a square, so it is a square footing, right? If this is a plan, if this is the plan of the footing, okay, so suppose this is your footing and this is the plan. Okay, so this is the plan. Suppose if this dimension is b, suppose the square footing, so the sides will be like b cross b. If one dimension, if suppose one side of the footing is b meter, suppose then like this. Okay, so b cross b. Okay, so because suppose, okay, so let the side each side be b meter, so that means it will be b cross b. So we can say it like this. So this is the ultimate load that the foundation can take. Okay, so we can say it like this, that is the ultimate bearing capacity. So ultimate bearing capacity, we can write it like this, right? So this is the ultimate load. If I divide this, if I divide the ultimate load by the area of the footing, that is Q ultimate load by the area, that is the V square, that is the area of the footing, we will get the ultimate bearing capacity, right? So Q ultimate, Q capital Q is 5500. Okay, so 5500 divided by B square. Okay, so this is actually the, you know, the bearing capacity, the ultimate bearing capacity of the footing, so kilonewton per meter square. Okay, this, so what is the equation for ultimate bearing capacity? QU is CNC plus Q dash NQ plus half into gamma dash n gamma. For square footing, I believe it is, this one becomes 0.4. So so this one, third part is 0.4 gamma b n gamma. Okay, So this is the bearing capacity, ultimate bearing capacity equations for a square footing, and this one is a questionless soil. Okay, so C equal to 0. That means C is equal to 0 over here. That means this part will be equal to 0. All right. So only this part remains, and Q dash. Okay, so we need to find out the effective overburden pressure at the foundation depth. Okay, at this level, at the level of foundation depth. That means at DF. So we know the unit weight. Unit how much? 18, and DF is how much? 2. That means 18 into 36. So that means Q dash is 2 into 18. DF is how much? It is DF into gamma. So it will be like, let me write it down like this. Okay, so gamma into DF, which is equal to Q dash. This one is Q dash in Q plus 0.4 gamma V in gamma. Okay, we know the values of all the parameters, right? So let me just put all the values of all the parameters into this equation. So gamma df. So gamma df is how much? So we can write it like this, right? This, if this is qu and this one is also qu, we can equate both the terms, right? So we can directly write it like this. So 5500 divided by b square is equal to this equation, right? So gamma df. So gamma is how much? Gamma is 18, df is 2, so 2 into 18. So it's 2 into 18 into NQ. NQ is how much? NQ is 81.3. So it is 81.3 plus 0.4 into, so 0. Gamma B and gamma. Gamma is how much? Gamma is 18. B is how much? Breadth of the footing we don't know. It is B. We need to find out that only. We need to find out the breadth of the footing, and we don't know. So let it be B. So gamma B and gamma. And gamma how much? It is 100.4. So let me write it like this. So 0.4 into gamma. Gamma is how much? 18 into B. We don't know the value of B into n gamma. N gamma is 100.4. Okay. So now we need to solve this equation. There is only one unknown, that is B. So after solving this equation, we will get the value of B. Okay. So let me just solve this equation. So if you just add, and if we just add and multiply both the terms, and if you just transfer this term from over to the right hand side, from left hand side to right hand side, you will get this equation. 5500 is equal to 2926.8 b square plus 722.9 bq. Okay, this equation. Okay, and if you can solve this equation by trial and error. Okay, so if you just solve this equation, you can get the value of b. So value of b will come out around 1.2 meter. Okay, so the square footing, the dimensions of the square footing is 1.2 meter into 1.2 meter. Okay, this is the dimension of the square footing. So I hope you have understood this problem. Please go through this problem for a couple of minutes. After that, I will proceed to the next question. So I hope you have all understood this current problem. So as I have told, you can always post your doubts in the forum, and also you can personally mail me, and you can also ask your doubts in the YouTube comment box. Okay, you can always do that, and the recordings of all the previous session and recordings of all the previous sessions and the recording of this session also will well, the recordings of all the previous sessions are already available on YouTube, and the recording of this particular session will also be made available later on. You can find the link in the NPTEL website also. You can always refer them anytime if you have, if you can also you can refer them anytime, okay, to clear your doubts. So now let us move on to the next problem. So this is the next problem, problem number 4. So let me read out the problem once. 2.5-meter wide strip footing is placed at a depth of 1.5 meter when the water table is at a great depth. Okay, so a strip footing of 1.5 meter wide is placed at a depth of 1.5 meter when water table is at the great depth. Determine the percentage decrease in the ultimate capacity of the same footing with a depth of 1.5 meter when water table rises up to a depth of 0.75 below the ground surface. Okay, let me read out the problem once again. 2.5-meter wide strip footing is placed at a depth of 1.5 meter when the water table is at a great depth. Okay, determine the percentage decrease in the ultimate bearing capacity. So we have been asked to determine the percentage decrease in the ultimate capacity of the same footing. Okay, same footing with the same depth of 1 meter when the water table rises up to a depth of 0.75 meter below the ground surface. Okay, so water table rises up in the second case. Okay, you have a footing, and then after that water table rises up to a depth of 0.75 below the ground surface. Okay, and take bulk and this bulk and saturated unit of soil is 17 kilonewton per meter cube. Unit rate of water is 10 kilonewton per meter cube. Phi is equal to 30 degrees, C is equal to 0, that means it is sand, NQ is 60 and gamma is 75. Okay, we have been asked to use Terzaghi's equation. Okay, so in the first case, initially the water table was at a great depth. Okay, initially the water table was at a great depth. Okay, so 2.5-meter wide strip footing is at a placed at a depth of 1.5 meter below the ground surface. Okay, this is the first case when water table is at a great depth. Okay, suppose there is the water table, it is at a much greater depth. Okay, so what will be the bearing capacity of the footing in this particular case? So ultimate bearing capacity of this particular case, in this particular case, Q is equal to, we can write it like this, right? Gamma dF in Q plus half into gamma b in gamma. This is a strip footing, and this is sand. The first part will be 0, like right, the CNC part, because C is equal to 0. Okay, so this is the ultimate bearing capacity equation for a strip footing in sand. Okay, so now if we let us put the values of all the parameters. So this is the first case. Okay, this is the first case, first dry case. Okay, first case or dry case. Okay, because water table is at a greater depth. So now let us put all the parameters into this particular equation. So gamma is how much? Gamma is 17. df is how much? Depth of the foundation is 1.5. nq is how much? nq 60 plus half into gamma. Gamma is how much? Gamma is 17. b is 2.5. n gamma is how much? It is 75. Now, if we solve this, we will get the value of Qu, that is ultimate bearing capacity of this particular case, and it comes out to be around 3124 kilonewton per meter square. Okay, this is the first case. So now in the second case, what happens is that in the second case, the water table rises up to a depth of 0.75 below the ground surface. Okay, so in the first case, in the first case, the this is the suppose it's footing 1.5 meter, right? 1.5 meter. This is the depth of the footing, and 2.5 meter is this the breadth of the footing, and water table is over here suppose. Okay, and after that the water table rises up to a depth of 0.75 meter below the ground surface. Okay, suppose over here because over here it is 0.75, and this is how much? It is 1.5 meter like before. This is 2.5 meter. Okay, so we need to find out the ultimate bearing capacity equation, ultimate bearing capacity for this particular case. Okay, so after that we can easily determine the percentage decrease in the ultimate capacity of the same footing. Okay, we can determine. So we need to determine the ultimate bearing capacity for this particular case when the groundwater table is at a depth of 0.75 below the ground surface. Okay, so now let us solve. Let us use the equation for ultimate bearing capacity. So for second case, it is, so we need to determine if the effective overburden pressure at this level, right? At this level, we need to determine the effective overburden pressure at the base of the foundation. So it is how much? It is 0.75, this part. Okay, 0.75 above the groundwater table, 0.75 into gamma plus this part also, which is 1.5 minus 0.75, or it is also 0.75. So that means this 0.75 into gamma plus this 0.75 into gamma submerged. Okay, yes. So let me write it like this. So it will be like gamma into dw plus gamma sat into df minus dw. Okay, this is the surcharge into nq, into nq, right? Into nq, to nq plus half into gamma submerged into gamma b n, this. Okay, so now let me just put the values of all the parameters into this equation. So qu second, it is how much? So gamma dw, gamma is how much? This part, gamma of this part, it is already given. Gamma bulk equal to gamma set. This is gamma, so it is 17. So it is 17 into this part. Okay, dw. This part is how much? It is 0.75. So into 0.75 plus this part is how much? Df minus dw. So 1.5 minus 0.75 is 0.75. So 0.75 into gamma submerged is how much? Gamma submerged is, gamma set is how much? It is 17. So 17 minus 10 is equal to 7 kilonewton per meter cube. Okay, so it is 7, right? Into nq. Nq is how much? Nq is 60. Nq 60 plus half into gamma dash. Gamma dash is how much? 7 into the gamma b, that is the breadth of the foundation, is how much? It is 2.5. Half into this gamma dash, that is gamma submerged, gamma b is 2.5 into n gamma. N gamma is how much? N gamma is how much? It is 75. So now if you solve this, you will get the value of qu for the second case. If you calculate this, qu comes out to be around 1736 kilonewton per meter square. Now you have bearing capacity, ultimate bearing capacity value for both the cases. So now you need to find out the percentage decrease. So what is the percentage decrease? Percentage decrease. It is how much? What is the ultimate bearing capacity of the first case? It is 3124. So 3124 minus of what is the ultimate bearing capacity for the second case? It is 1736. 1736 divided by first one, 3124 into 100. So this comes to be around 44.4%. Okay, this is the answer. Okay, so please go through this. So I hope you have understood this problem. Please go through this problem for a couple of minutes. After that, I will proceed to the next problem. Okay. So I hope you have all understood this particular problem. So now let us move on to the next one. So let us move on to the next problem. So what is the next problem? Let me read out the problem first. So a rectangular footing of size 2 meter by 3 meter is founded at a depth of 1 meter in a homogeneous C5 soil deposit. Okay, so a rectangular footing of size 2 meter by 3 meter is founded at a depth of 1 meter in a homogeneous C5 soil deposit. The water table is at a great depth. The unit weight of soil is 18 kilonewton per meter cube, and an eccentric vertical load is applied to eccentricity with EL is equal to 0.5 meter and EB is equal to zero point 0.4 meter. Okay, determine the effective area of the footing. C is equal to 100 kPa, phi is equal to 20 degrees. Use Heiter Anders approach. Okay, so see, so there is a rectangular footing of 2 meter by 3 meter. It is founded at a depth of 1 meter in a C5 soil deposit. Okay, fine. The water table is at a great depth. The unit weight of soil is given, and here an eccentric vertical load is applied. Okay, to a eccentricity. Okay, with EL, that is at eccentricity along the length is 0.5 meter and eccentricity along breadth is 0.4 meter. Okay, so we have been asked to determine the effective area of the footing. C is equal to 100 kPa and phi is equal to 20 degrees. So we have been asked to use Heiter Anders approach. Okay. So suppose this is the plan of the footing, the top view of the footing. It is like this. And if this is the length of the footing and this is the breadth of the footing, okay. Suppose this is the breadth and this is the length of the footing, and this is the center line. Suppose the eccentricity, so let us point out the eccentricity. EL is 0.5 meter, that is along the length. EL is 0.5 meter. Suppose it is over here, this is EL, and this one is suppose EB. Okay, this one is EB is how much? 0.4 meter. Okay, suppose this is the point where the load is acting. Okay, it is like this. Okay, the EB is equal to 0.4 meter, EB is equal to 0.5 meter, EL. Okay, so now we need to find out the effective area of the footing. So in this particular case, the effective zone will be like this. The effective zone will be like this. Okay, this is the effective zone, and here the load is active. Okay, and now this particular length of the length of this particular triangle, because the zone is like a triangle, the effective zone, the length of this particular side is, suppose it is B1, and length of this particular side becomes L1. Okay, this one is along this length and this one is along this breadth. Okay, L1 and B1. Okay, so now we need to check some conditions. So we know the value of EB is how much? EB is 0.4, EL is 0.5, B is 2 meter and L is 3 meter. Right, all these informations are given in the particular question, in this particular question. All this information are given. Okay, so now we need to check if EB, we need to check EB and EB by B. Okay, so EB by B, how much it is? So 0.4 by 2, it is around 0.2. This is one greater than 1.6. Okay, and EL by L, it is how much? EL by L is 0.5 by 3, it is 0.167, and it is also in it is equal to 1 by 6. Okay, so for this particular case, the effective area is like this. Okay, we need to check that before before drawing this effective zone. Okay, you need to check these conditions. Okay, so now after that we need to find out these two sides, the length of these two sides, B1 and L1. Okay, the sides of the triangle, we need to find out the sides of the triangles. Okay, so it is B1 is equal to B into 1.5 minus 3 into EB by B, this one. Okay, so it is like this. So B is how much? B is 2 meter to 1.5 minus 3 into EB. EB is how much? EB by EB, EB is zero point 0.4, B is how much? B is 2 meters. So 0.4 by 2. So 0.4 by 2, this. So this comes out to be 1.8 meters. Okay, and L1. L1 is how much? L1 is L 1.5 minus 3 EL by L. And so it is like this. So L is how much? L is 3 meter. It is 1.5 minus 3 into zero point 0.5 EL. EL is how much? EL is zero point 0.5. So zero point 0.5 and L is 3 meters. So 0.5 by 3, and then this comes out to be 3 meter. And this L dash, okay, this L dash is the maximum of B1 and L1. Okay, maximum of B1 and L1. Okay, so L dash is around, so is 3 meter. Okay, so L dash is equal to 3 meter. Okay, so now what is the area of the triangle? So for effective area, and this one is L dash, the length, and breadth is 1.8. So it is like this. So half into base into length, half into L into B. So here the length is how much? Length is 3 meter and the breadth is 1.8 meters. So half into 1.8 into 3, then this is the effective area of the triangle. Okay, so and it comes out to be around 2.7 meters square. So this is the answer. Okay, so I hope you have understood this particular problem. Okay, so I am giving you a couple of minutes to understand this problem, to go through this problem. If you have any doubt, you can tell me. So now let us move on to the next problem. So let us move on to the next problem. So first of all, let me read out the problem once. So a rectangular footing of size 2 meter by 3 meter is founded on a homogeneous Cephei soil deposit. 3000 kilonewton load acts at an angle of 10 degrees to the vertical at the center of the foundation. C equal to 75 kPa, phi equal to 25 degrees. The net ultimate bearing capacity of the foundation is 1250 kPa. Determine the factor of safety against the bearing and sliding. And take the frictional angle between base and soil as 0.85 and cohesion and the addition between the base of the foundation and The soil is 0.7 C, neglect passive resistance. Okay. So in this particular case, a rectangular footing of size 2 meter by 3 meter is founded on a homogeneous severe soil deposit. Okay. 3000 kilonewton load acts at an angle of 10 degrees to the vertical at the center of foundation. Okay, the load is inclined. So that means it will have two components, horizontal and vertical. So due to which the vertical component, okay, so we need to check the factor of safety against bearing by involving that vertical component, and the horizontal component will try to slide the foundation. So so we need to check the factor of safety against sliding by using that horizontal component. Okay, so delta base equal to 0.85 and C addition of base is 0.7 C. Okay, so huh, so it is like this actually. So let me draw it first. So suppose this is your footing. Suppose this is our footing. Okay, and low and this is the center line of the footing, and load is acting like this. Okay, it is 10 degrees to the vertical. Okay, it is like this. So 10 degrees to the vertical. So that means it will have two components like this and like this. Okay, horizontal and vertical components. Okay, this is 3000 kilonewton, and suppose so H is will be like 3000 sine 10 degree, and this one V is equal to how much? 3000, and V will be how much? V will be 3000 cos 10. Okay, the vertical component. Okay, so we need to use this particular component to check the factor of safety against bearing because it is acting vertically, and we need to use this component to check the factor of safety against sliding because this particular force will tend to slide the foundation. Okay, so first of all, let me solve for to determine the factor of safety against bearing. Okay, so factor of safety against bearing. So factor of safety against bearing, it is given by AQNU by V. Okay, and QNU is how much? The alternate bearing capacity is how much? It is 1250 kPa. Okay, so so let me write it down on the data over here. QNU is how much? QNU is 1250 kPa. Okay, 1250 kPa. This area of the footing is how much? It is 2 meter by 3 meter. Okay, so 2 into so 2 into 3 equal to 6 meter square. Okay, this vertical component is how much? It is this vertical component is how much? It is 3000 cos 10 degrees. 3000 cos 10 degrees. Okay, so now we need to put all the parameters into this equation. Okay, so 3000 cos 10 degrees, it comes to be around 2954.4 kilonewton. Okay, now let me just put all the parameters into this equation. So this equation, okay, so it will be like Fs will be like A is how much? A is 6 into QNU is 1250 and V is how much? It is 2954.4. Okay, this. So now if you calculate this, you will get the value of factor of safety and bearing. Okay, it comes out to be around 2.54. Okay, and this is greater than 1, so it is, so the foundation is safe against bearing. Okay, so, and after that we need to find out, okay, please wait a bit. Okay. Let me just share my screen once again. Okay, so let me write it down once again. Okay, I have there was some issue. So where was I? So area. So area of the footing is how much? So area of the footing is 2 meter by 3 meters. So that means 2 into 3. It is, since it is a rectangular footing, so area is 6 meters square. Right? We know the value of V is how much? V is the vertical component. V is this 3000 cos 10 degrees. Okay, so 3000 cos 10 degrees, and this comes to be around how much? 2954.4 kilonewton. So 2954.4 kilonewton. Okay, now let me just put all the parameters into this equation. Okay, so factor of safety against bearing. How much? It is how much? So A is how much? The area of the footing, it is 6 into QNU. The net ultimate bearing capacity is 1250 kPa. Divided by vertical component of the force of the load is 2954.4 kilonewton. So 2954.4 kilonewton. If you solve this, you will get the value of factor of safety against bearings, and this comes out to be around 2.54. And this is greater than 1, so so the footing is safe against bearing. Okay, so we need to find out now. We need to find out the factor of safety against sliding. So we need to find out the factor of safety against sliding. Okay, so factor of safety against sliding. So there is the equation. Equation is what? So there is the equation to find out the factor of safety against sliding. Okay, so the resisting force against sliding. So what will be the resisting force? See here, when this horizontal force will try to slide this foundation in this direction, there will be a shearing force under shearing resistance over here at the junction between the soil and the the footing, because cohesion is there. Okay, so there will be a shearing resistance. Okay, you need to find the resistance and compare that with this the horizontal resistance, the horizontal force. Okay, in this way you can easily get the factor of safety against sliding. Okay, so factor of safety sliding, factor of safety against sliding. So what is the shearing resistance? The resistance against the horizontal load, it is given by A into C, the area of the foundation, into C means the adhesion, plus the vertical component into tan of delta. Okay, that is the frictional angle between the uh, footing and the soil. So tan delta divided by the horizontal load. This particular this the numerator is the the resistance, the shearing resistance against the horizontal load. Okay, so now let me just put all the parameters into this particular equation. So A is how much? A is 2 into A is how much? 2 into 3. Okay, that means 6. CA is how much? CA is 0.7 C. C is how much? C is 75. So zero point 0.7 into 75. So 0.7 into 75. Okay, plus vertical component. Vertical component is how much? Hmm. Vertical component is how much? It is 3000 cos 10. So 3000 cos 10 comes to be around 2954.4, 2954.4 kilonewton. Okay, into tan of delta. Tan of delta means delta is how much? Delta is zero point 0.8 into 5. So zero point 0.8 into 25. So tan of zero point 0.8 into 25. So this is the value of the resistance against the horizontal load divided by the horizontal component. So what is the horizontal component? So horizontal component is how much? It is 3000 sine 10. So it is 3000 sine of 10 degrees. So now if you calculate this equation, you will get the value factor of safety against sliding. So the factor of safety against sliding comes up to be around 2.67, which is greater than 1. So the footing is safe against sliding. So I hope you have understood this particular problem. So I hope you have understood this. So I hope you have understood this particular problem. And there is another problem left, the last problem. Let me just solve that problem. Okay, so according to Hansen's theory, determine the ultimate bearing capacity of a strip footing of width 3 meter resting on top of a slope such that df is equal to 0. Fine. So a footing is resting on top of the slope, and we need to determine the ultimate bearing capacity of the strip footing using Hansen's theory. The slope is making an angle of 15 degrees with the horizontal, and the friction angle of soil is 40 degrees. C is equal to 0, N C is equal to 64.1, and gamma is equal to 79.5. The load is acting vertically at the center of the footing. Soil compressibility, water table effects are neglected. Foundation base is not tilted. The unit weight of soil is 18 kilonewton per meter cube. Okay, so what is happening over here? So there is a strip footing of width 3 meter resting on top of a slope, and the slope is making an angle of 15 degrees. The slope is making an angle of 15 degrees with the horizontal. So that means, let me draw it first. This is the slope. Suppose this is the slope of 15 degrees, and here there is a foundation like this. Okay, there is a strip footing of width 3 meter. Okay, it is resting on top of a slope such that df is equal to 0. Okay, so df is equal to 0. The slope angle is 15 degrees. This is the slope angle, and the friction angle is how much? It is 40 degrees. C is equal to, question is equal to 0. That means this is a sandy slope. In Q, the bearing capacity factor is 64.1. In gamma is also how much? 79.5. Okay, the load is acting vertically like this at the center of the footing. Soil compressibility, water table effects are neglected. Foundation base is not tilted. Okay, that means the base is horizontal. The unit weight of soil is how much? It is 18 kilonewton per meter cube. So we need to determine the ultimate bearing capacity of the strip footing. Okay, so there will be factors. So some factors will be there due to this slope, due to the sloping ground. Some factors will be incorporated. Okay, so let me just write down the bearing capacity equation of Hansen. So according to Hansen's theory, QU is equal to, for sandy soil, and since the footing is on the top of the slope on the surface, so that means the surcharge part will be 0, right? The overburden part will be 0 because the footing is resting on top of the slope on the surface. So that means only the third part of the bearing capacity equation will be there. So that is half into gamma b in gamma, shape factor, depth factor, inclination factor, compressibility, sloping ground, then the base tilt base factor. Okay, so now this for strip footing, this S gamma, D gamma, I gamma, all these are 1, and also we have been asked to uh, also we have been in the question we have been asked to neglect the compressibility effect and water table effect. So that means C gamma we can also write it like 1, and since the base is not tilted, it we can, so B gamma is also 1. Okay, so only this G gamma will be there. Okay, only G gamma, and this G gamma we can find it from this chart. So G gamma for ground. Okay, since this is the slope, the base is not tilted. Okay, so that means we need to use this one only. Now, because the base is not tilted, base is horizontal, only the ground is tilted. Ground, it is a sloping ground, so we need to use this for G gamma. For G gamma, the sloping factor. Okay, and so G gamma is how much? It is 1.0.5. This one will put 10 beta to the power 5. This, okay, so it is how much? 1.0.5 tan of 15 degrees. The angle of solve is 15 degrees to the power 5, and this comes out to be 4.487. Okay. So after that, we need to put all the parameters into this equation. Okay. So half gamma b n gamma and g gamma. So we know the value of gamma b n gamma and g gamma. So qu is equal to half into gamma is how much? So gamma is 18 degree, 18 kilonewton per meter cube. Gamma b is how much? B is 3 meter. So gamma b and gamma is how much? It is 79.5. Gamma b and gamma, and g gamma is over there. Okay, so that means gamma into this half into gamma into b into n gamma into all the factors and the factors, all the factors are 1. Only g gamma will be there. Then g gamma is 0.487. If we calculate this, we will get the value of q, and it comes out to be around 1045.35 kilonewton per meter square. Okay, so this is the answer. So I hope you have all understood this particular problem. So this is the last problem of today's session. So I hope you have all understood all the problems. If you have any doubts, you can either mail me or either post your doubts in the NPTEL forum. You can also post all the doubts in the comment box of YouTube videos. You can also post your doubts over there. And the recording of today's session will also be made available on YouTube, and the link will be given in the NPTEL site. Okay, so that is all for today. See you in the next session. Okay, so have a nice evening. Goodbye.